Hello students, welcome to Educate. Today we are going to study lens maker's formula. So let's see what it is. So here we are considering a biconvex lens. First we will consider this refracting surface. For this picture will be like this, and then we will consider this refracting surface means ABC, then ADC, and then we will apply the formula that we have already derived. So when refraction is taking from this surface, so we will write this relation N1 divided by OB means object distance, plus N2 divided by BI1 equal to N2 minus N1 divided by BC1. And then image will be formed over here, I1. And now this I1 will behave like object for second surface, and its final image will be formed over here. So for second surface, we write the relation minus N2 upon di1 plus N1 upon di1 di equal to N2 minus N1 divided by dc2. dc2 is radius of curvature of second phase, right? Now if we do certain assumptions, then we can write bi1 equal to di1. It means lens is very thin. Distance measured from B or D will be same. So after putting those values, and we can add the two equations, this 9.17 and 9.18. So it will give N1 upon OB plus N1 upon DI equal to N2 minus N1 times 1 upon BC1 plus 1 upon DC2, right? So here we mix other assumptions, like we assume that object is at infinity, which means OB will be infinity, then its image will be formed at focal length, right, F or DI. So DI will be equal to F. So if we write that value here, this term will become 0 and DI is F. So N1 upon DI equal to N2 minus N1 times 1 upon BC1 plus 1 upon DC2. And basic definition of focal length is given here. That is simple. Here BC1 is radius of curvature, which is positive, and DC2 will be also radius of curvature of this surface, and that will be negative. So we can put those values here. So this will become 1 upon R1 minus 1 upon R2. And one more step we can take, we divide each term by N1. When we divide each term by N1, this will become N2 upon N1 minus 1. So we can write N2 upon N1 as N21 minus 1 equal to 1 upon R1 minus 1 upon R2. But we know 1 upon V minus 1 upon U equal to 1 upon F. So in place of this, we can write 1 upon V minus 1 upon U. So N1 upon OB plus N1 upon DI is N1 upon F we have taken, and for thin lenses we write 1 upon V minus 1 upon U equal to 1 upon F. So the previous equation that we have got, like 1 upon F equal to mu minus 1 upon R1 minus 1 upon R2, is called lens maker's formula. Now here the rules for image formation are shown that you have already studied in lower level how images are formed. So I'm not going to explain these things in detail. Here there is one good question for you. Question says, a magician during a show makes a glass lens with n equal to 1.47 disappear in a trough of liquid. What is refractive index of the liquid? Could the liquid be water? Very simple rule is there. If any substance disappears in a liquid, then refractive index of substance could be either equal to that of liquid or less than that of the liquid. So here what is happening? The refractive index of the liquid must be equal to 1.47 in order to make the lens disappear. This means that N1 and N2 will be same. So from previous formula, this gives 1 upon f equal to 0 or f equal to infinity. So we can say that this lens will behave like a plain glass sheet, and it can't be water. It could be glycerine, because water has a refractive index 1.33, and here refractive index of the material is 1.47. So of course, if it is disappearing, it means liquid must have a refractive index either equal to 1.47 or that more than that. Now we are going to define power of a lens. So here, power of a lens is a measure of the convergence or divergence which a lens introduces in the light falling on it. Clearly, a lens of shorter focal length bends the incident light more while converging it in a case of convex lens and diverging it in case of a concave lens. The power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of parallel light. So tan delta we can define perpendicular upon base, so h upon f. If h equal to 1, then tan delta is 1 upon f, or delta equal to 1 upon f for smaller value. So power is generally defined as 1 upon focal length, and unit of power is diopter. For convex lens, power is positive, and for concave lens, power is negative. If we say that power is say plus 2.5 diopter, so we write this here 2.5 equal to 1 upon f, then f will be 1 upon 2.5 meter, and then we can calculate to get f 40 centimeter. Similarly, for converging lens, we can find the power. Here there is one question for you. Let's read it together and try to understand what it says. If f equal to 0.5 meter for a glass lens, what is the power of the lens? We have studied that P is equal to 1 upon f. So if you divide it, so you will get 2 diopter. The radius of curvature of the faces of double convex lens are 10 cm and 15 cm. Its focal length is 12 centimeter. What is refractive index? The formula that we have derived, 1 upon f equal to mu minus 1, 1 upon r1 minus 1 upon r2. From there we can get the value. And the next question is, a convex lens has 20 centimeter focal length in air. What is the focal length in water? So here, in this case, what do? We write the ratio n2 upon n1 as you have seen. Here same thing is explained. First case is given power 2 diopter. Second case, focal length is given 12 centimeter, R1 is given 10 centimeter, R2 is minus 15 centimeter. So we can write the formula 1 upon f equal to n minus 1, 1 upon R1 minus 1 upon R2. As I told you, R2 will be in this side, so it will be negative. So after putting values, we will get n equal to 1.5. Then second case, for a glass lens, in here n2 is 1.5, n1 is 1, f equal to 20. Hence the lens formula, as we have studied, 1 upon f equal to here n2 minus n1. So n2 is 1.5 and 1 is 1, so difference will be 0.5, and 1 upon r1 minus 1 upon r2. So we can find this relation for 1 upon r1 minus 1 upon r2 from here. Similarly, for glass lens in water, we will write 1.5 minus 1.33. Again, we will get one relation, and then we can solve the two, this relation and this relation. So after that, we will get f equal to 78.2 centimeter. This is good question. Now we are going to see what happens when lenses are put in contact. If both lenses are of same type, then their focal lengths will be added by writing in reverse way, like 1 upon f will be equal to 1 upon f1 plus 1 upon f2. So, and powers will be directly added. If one is converging, another is diverging, then with sign we will write focal length, hence power will be subtracted. So that is obvious. So here same thing is given for two lenses, 1 upon f equal to 1 upon f1 plus 1 upon f2. And if there are many lenses in contact, so 1 upon f equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3. Here sign of f must be considered. If it is concave, in that case negative sign. If it is convex, then positive sign. And if we convert it into power, so p will be p1 plus p2 plus p3, etc. And keep in mind, if we are calculating power, so we are adding. But if we are finding magnification, then it will get multiplied. This is very important concept. Don't get confused between the two. Here we have a very important question in which three lenses are there. Their focal lengths are given and their separations are given, and we have to find out the position of the image formed by lens combination. So what will be position of the final image? So for that purpose, we take first lens and we remove others. So here object distance is 30 centimeter, its focal length is 10 centimeter, and we apply normal formula 1 upon v minus 1 upon u equal to 1 upon f. So here object distance is given as 30 centimeter, which will be negative, f is positive. After putting the values, we will get v1 equal to 15 centimeter. It means what? Distance of image will be in this direction, here 15 centimeter distance. So we assume that this lens is not there, and here there is final image of this object. Now we have to consider this lens. So this lens is at distance 5 centimeter from this lens. So since the image by the first object, by first lens was formed here 15 centimeter, so object distance for this lens will be just 10 centimeter. Then again we do calculation with focal length minus 10 and object distance 10 centimeter positive, right? So if we do calculation this time, then what do we get? We are getting v2 equal to infinity, right? If v2 equal to infinity, then third case is simple. If object is at infinity, then its image will be formed at the focus. So finally we consider third lens, and whose image will be formed at 30 centimeter, right? So it is simple. Now we are going to see refraction through a prism. In case of prism, if you remember, here this is angle of prism, this is normal, this is second normal, and this is incident ray. This angle is angle of incidence, right? And this will be angle of refraction. Here this is also angle of refraction, this is angle of emergence. And if we consider that this ray goes undeviated, so it will follow this path, and this is emergent ray. If we extend it backward, so they are meeting at point M, and here angle of deviation is formed. So now we are going to relate delta E, R1, R2 and I. But keep in mind, in case of minimum deviation, these two angles will be same, R1, R2 will be same, I and E will be same. So on the basis of these assumptions, we will try to derive the formula. So here, first thing, in the quadrilateral AQNR, what do you observe? This angle is 90 degree. This angle is 90 degree. So only A and N will be left. So we can say A and N will make 180 degree. And then we consider this small angle R1 plus R2 and N again. So R1 plus R2 plus N will give 180 degree. So we can equate the two equations. So from here, because A plus angle QNR is 180, R1 plus R2 plus QNR is 180. So from there we will get R1 plus R2 equal to A. Similarly, we can write deviation by applying formula. Here external angle will be sum of two remote internal angles. So this angle, suppose here we take x, this y, and then we evaluate. So delta will be I minus R1 plus E minus R2. And then finally it comes out to be delta equal to I plus E minus A, because from here we will get R1 plus R2 together with minus sign, so A. Now we can use the concept of a minimum deviation. So as I told you, in case of minimum deviation, E and I will become equal, R and R1 and R2 will become equal. So from here we will get R equal to A by 2, and here we will get what? E, this will become equal, right? So we will get value of delta. But our concern is to get I. So take A to this side. So 2I equal to delta plus A, or I equal to A plus delta divided by 2. So we have got R equal to A by 2 and I equal to delta plus A by 2. And then we apply the formula. What is formula? Mu equal to sine I upon sine R. So if we put those values, then the refractive index will be sine A plus delta, which is minimum deviation divided by 2 divided by sine A by 2, right? So up to here there is no problem. Here in graph it is depicted that when I equal to E dash, this is case of minimum deviation, right? So this is graph of minimum deviation. So how to find this is angle of deviation, and at this point this is angle of incidence. So this is the point where minimum deviation occurs, and after that deviation increases. So here we can do further assumption if we say that angle of prism is small. In that case sine theta can be ignored, then we will get n equal to sine will land with the A plus dm by 2 divided by A by 2. So after simplifying, we will get delta minimum is equal to refractive index minus 1 times A. So we will see some numericals on it later on, or you can recently see, suppose we take some questions, like suppose delta M is given say 30 degree, and angle A, prism angle is say 60 degree, and we have to find out what is refractive index mu. So sine of A plus delta M whole divided by 2 divided by sine A by 2. We put the values. So here it will become sine 90, which is 1, and sine A by 2. A by 2 means 30 degree. So this will give 1 by 2, so 2. Like this. Now we are going to see some optical instruments. So optical instruments like microscope, simple microscope, compound microscope, telescope, etc. we will observe one by one. So simple microscope means just magnifying glass. So here diagram of simple microscope is shown. Object is placed between focus and pole. So its virtual and erect image is formed at least distance of distinct vision, right? And here when object is at focus, then its image will be formed at infinity. So two situations we deal, and we will find out the expression for each one. And you know that least distance of distinct vision is 25 centimeter. So here m equal to, you know, in case of lens it is v upon u. So v and 1 upon u we can write in terms of 1 upon v minus 1 upon f. That gives 1 minus v upon f. Now final image is formed at least distance of distinct vision, and it is to the left. So we can write in place of v minus d. So minus minus will become plus. So magnification will be 1 plus d upon f, right? So here it is simple. Tan theta in second case, when image is formed at infinity, we can also get another relation. In that case, here 1 will not appear. M will be equal to d upon f, right? So the same thing is explained here. You can read it, you will understand. So it is just basic thing. Now we have to study the compound microscope. But before that, I would like to tell you one example. Like you are given simple microscope, right? And you know D is equal to 25 centimeter. Focal length is given as 5 centimeter. And we assume that image is formed at first case D, second case at infinity. So what is formula for magnification? M equal to 1 plus D upon F when image is formed at least distance of distinct vision. So this is first case. So we write here 1 plus 25 upon 5, that will give 6, right? And if image is formed at infinity, then we have M equal to D upon F. So we can write D 25 upon 5, so it will be 5. I think you have understood. Now we are going to see another thing. This is case of compound microscope. Here we have taken two lenses. Objective lens whose focal length is smaller, and this is eyepiece whose focal length is larger. Focal length of object is f(o). Here object distance is u, and image is formed at this point. This is b dash a dash image due to objective, and then this image b dash a dash will work as object for the eyepiece, and final image will be formed at least distance of distinct vision from the eyepiece, right? So this is basic. Now we are going to do some calculations. So magnification produced by first lens will be h dash upon h, and that will be L upon FO, right? And the logic is very simple. We have used tan beta, as you know, h upon FO or h dash upon L, where h dash will be the size of the first image and h being the size of object, and f0 is the focal length of objective. And now the same image will behave as object for the this eye lens, and then its final image will be formed here. So again we are going to apply formula for magnification, and as we have already studied that when image is formed at least distance of distinct vision, then ME means magnification of eye lens will be equal to 1 plus D upon FE, right? And if image is formed at infinity, in that case 1 will not be there, it will be D upon FE only. So ME is this. Now we are assuming that final image is formed at infinity. So here two relations are possible. First we will write this thing, ME will be 1 plus D upon Fe, and in second case we will take M equal to D upon Fe, right? So two relations are possible. One will be M equal to MO into ME will be L upon FO times here 1 plus D upon Fe, and second case when final image is formed at infinity, then this will be the result, right? So here one example is given that you can read. Example says, with an objective with f0 equal to 1 centimeter and an eyepiece with focal length f equal to 2 centimeter and a tube length of 20 centimeter, the magnification is L is a tube length, right? So M equal to M0 ME, tube length is given as 20, FO is 1 centimeter, least distance of distinct vision is 25, and FE is given as 2. we simplify, so we will get 250. Clearly, magnification is large as compared to the simple microscope. Now we are going to see telescope. So in case of telescope, here what is difference? In previous case, in case of compound microscope, we have taken objective lens of short focal length, whereas eyepiece has large focal length. But in this case, in case of telescope, we will do the reverse. Objective will have large focal length so that it can gather more light, and eyepiece will have small focal length, right? And then we can define magnifying power in terms of ratio, the angle beta subtended at the eye by the final image to the angle alpha the object subtends at the lens on the eye. So here m equal to beta upon alpha, and beta is h upon fe, and this alpha will be h upon fo. So we get fo upon fe, means magnification produced will be the ratio of focal length of objective divided by focal length of eyepiece, and obviously it will be more than 1. Here diagram is shown. This is objective lens whose aperture is larger and whose focal length is large as compared to the objective lens. This is objective, and here we assume that object is at infinity. Of course, we are viewing the objects at far off distances, so they are assumed to be at infinity. So rays will be parallel and they will be focused at the focus of objective. That is why here image is formed, and then this object will behave like the object for this image will behave like object for the eyepiece, and being situated at its focus, again its image will be formed at infinity. So that thing is shown here, and some other specifications are given that you can read. Then comes next point. Here reflecting telescope or Cassegrain type telescope is shown, in which there is a mirror. This is called secondary mirror, and this is objective mirror. This is paraboloidal, right? So that marginal rays may also get focused, and this is eyepiece, right? So here rays are coming like this, and they are reflecting by this mirror, and final image formed at eyepiece. So here the detail of this thing is omitted from syllabus, so we have to study only this thing that we have gone through. I think you have understood the chapter very well. Let's have a quick summary of the lesson, then we will do numericals in next lecture. Reflection is governed by the equation angle of incidence equal to angle of reflection. Here it is refraction. So in case of refraction, if you remember, sin I upon sin r equal to refractive index, but in case of reflection, angle I equal to angle r, right? And you know the phenomena of total internal reflection, in which if angle of incidence is more than critical angle, in that case the light ray comes back in the same medium. But the necessary condition is that ray must go from denser to rarer medium, and uses of total internal reflection like optical fire and other cases are also there. Then we have studied lens maker's formula, refraction. This is basic mirror equation, that also you know. Sign convention, you know that distances to the left of the mirror or lens will be negative, and to the right of mirror or lens will be positive. Upward above the axis will be positive, below the axis will be negative. And then mirror equation, you know, 1 upon v plus 1 upon u equal to 1 upon f, and the lens equation will be 1 upon v minus 1 upon u equal to 1 upon f. And then we have derived the relation for prism. If its refractive angle is a, minimum deviation is delta m. Then refractive index of the prism will be given by sine a plus delta m divided by 2 whole divided by sine a by 2. And then we have studied refraction at the spherical surfaces like n2 upon v minus n1 upon v equal to n2 minus n1 upon r. And then we apply thin lens formula, and finally we arrive at lens maker's formula 1 upon f equal to n2 minus n1 divided by n1 1 upon r1 minus 1 upon r2. And then we have defined power, which is 1 upon f, and its unit is diopter. And in case of a diverging lens it will be negative, whereas in case of converging lens power will be positive. When there are many lenses and they are in contact, in that case total power will be sum of their individual powers, and the total focal length will be found by inverting the focal length and then adding them. And then dispersion is the splitting of light in different colors. And then comes magnifying power of simple microscope is given by m equal to 1 plus d upon f, where d is 25 centimeter. And if image is formed at infinity, then m equal to d upon f. In case of compound microscope, magnifying power will be given by me into mo, and me will be 1 plus d upon fe. Then we can write m equal to l upon fo into d upon fe, where fo is focal length of objective, FEE is focal length of eyepiece, D is least distance of distinct vision, and L is length of the tube. Then magnifying power of telescope, we have studied m equal to beta upon alpha, that is FO upon FE, right? And then here there are certain laws that you can revise. The laws of reflection and refraction are true for all surfaces and pairs of media at point of incidence. And there are other points also that you can study. I think you have understood. So in the next lecture we will do numericals based on it. Thank you for watching. Team Educate.